Welcome to Lecture 17, Section 4.2 of the text Elementary Linear Algebra by Ron Larson, 7th edition, Cengage Learning. Vector spaces. This is Dr. Gilbert, Eyabi. Vector spaces. Let V be a set on which two operations, vector addition and scalar multiplication of vectors, are defined. V is a vector space if the following axioms are satisfied for every vectors u, v, omega in V and every scalar c and d. Property number 1, axiom number 1. U plus V is a vector in V, i.e. closure under addition. U plus V equals V plus U, that's commutativity with respect to addition. U plus V, all parentheses, plus omega equals U plus parentheses V plus omega. Associativity with respect to addition. Existence of an additive identity, existence of an additive inverse, closure under scalar multiplication, distributivity in the sense of C being a scalar, U and V vectors. So C into U plus V equals CU plus CV. And C plus D parentheses or U equals CU plus DU. Basically, write distributivity, but do not forget C and D are scalars. Then we have associativity with respect to multiplication, but do not forget C and D are scalars and U is a vector. And lastly, we have the existence of a scalar identity, which is 1. So 1 times U equals U, which equals U times 1. So if a set satisfies all these axioms, and of course the two operations vector addition and scalar multiplication must be defined on that set V, if such a set satisfies all the 10 axioms, then we conclude that that set is a vector space. What does that mean? So if I give you a set, maybe the set of polynomials of order 5, and you're asked the question, is this set a vector space? What you simply do is go through all the 10 properties and verify if they hold. If these properties hold, then we conclude that such a set is a vector space. If it does not, then sorry, it's a beautiful set, it looks good, but it is not a vector space. Now, I want you to verify which of these are vector spaces and which are not. All 2 by 3 matrices, all polynomials of degree 2 or less, continuous functions, the set of integers, the set of second degree polynomials, the set of all 2 by 2 non-singular matrices with the standard operations. And if you have forgotten what the standard operations of vector addition and scalar multiplication are, we would show you that before the close of this lecture. Here is a summary of some very important vector spaces. Number 1, the set R of all real numbers, R squared, the set of all ordered pairs, 2-dimensional planes. R3, the set of all ordered triples, Rn, the set of all ordered n tuples, and C, negative infinity, infinity, the set of all continuous functions defined on the real number line, which is from negative infinity to infinity, and Cab, recognize this to be the closed interval AB, is a set of all continuous functions defined on the closed interval AB. P is the set of all polynomials. Pn, the set of all polynomials of degree n. M Mn, the set of all m by n matrices, and Mnn, the set of all n by n square matrices. Again, how do we verify that these are vector spaces? Pick any one of them and verify if all 10 axioms are satisfied using the standard operations of vector addition and scalar multiplication for each of these sets. Here are some properties of scalar multiplication. Let V be an element in big V, where the little v is a vector and big V is the vector space, and let C be any scalar. Then the following are true. 0 times V equals 0. This 0 here is a scalar and this other 0 is a vector. C times 0 equals 0. This C is a scalar, this 0 is a vector, and this other 0 here is a vector. Now, if C times V equals 0, where C is a scalar and V is a vector, and this 0 here is a vector, then we have that C equals 0 or V equals 0, i.e., either the scalar is 0 or the vector has to be 0. And negative 1, which is a scalar quantity, times V equals negative V. I would leave the proof of all 4 properties as simple exercises for serious students. You can ask me questions about this in class if you want to. Okay, before we close this lecture, let's look at the problem in detail and verify if a given set is a vector space, i.e., we are going to check if all 10 axioms are satisfied using the standard operations in the particular vector space. Okay, so define S to be the set X 2x, which is a subset of R squared. It has a certain peculiarity. The elements in S are of the form X 2x. For example, the vector 1, 2 would be in S. The vector 2, 4 would be in S. The vector 3, 6 will be in S, and so on and so forth. But for example, the vector 1, 1 is not going to be in S. So S is the set of all vectors of the form X 2x. The question is, using standard operations in the vector space R squared, is S a vector space? Now, before we get into this, let's quickly remind ourselves what the standard operations of addition and scalar multiplication in R squared are. So if A, B, C, D are vectors in R squared and alpha is in R, then addition is defined by AB plus CD equals AC plus BC, and alpha into AB equals alpha A comma alpha B. So this is the standard definition of addition in R2, and this is the standard definition of scalar multiplication in R2. Verifying property number 1, closure under addition. Let U equals x1 to x1, V equals x2 to x2, omega equals x3 to x3, all elements of S. Now U plus V equals, this is my U and that is my V, and I'm using the standard definition of addition of vectors in R2. So that will be x1 plus x2 at the first component, 2x1 plus 2x2 at the second component. Factorize out my 2. I end up with x1 plus x2 comma 2 into x1 plus x2, which equals x wiggle comma 2x wiggle. X wiggle equals x1 plus x2. x1 is a real number, x2 is a real number. The sum of two real numbers is a real number, so x wiggle must be a real number. Therefore, my final vector is in S. Therefore, closure under addition holds. Property number 2, axiom number 2. We have to verify commutativity with respect to addition. U plus V, this is my U and that is my V. Component-wise addition, that gives me x1 plus x2, 2x1 plus 2x2. x1 and x2 are real numbers. There is commutativity in R. So x1 plus x2 is the same as x2 plus x1. Similarly, 2x1 plus 2x2 is the same as 2x2 plus 2x1. Now I can use again my definition of vector addition, the standard definition, and this breaks down to x2, 2x2, x1, 2x1. But this is V and that is U, so I just prove that U plus V equals V plus U. Therefore, we claim that commutativity under addition holds. Remember, we have 10 properties. 2 down, 8 to go. Property number 3, associativity with respect to addition. U plus parenthesis V plus omega, that is my U, that's my V, that's my omega. I start off by adding V plus omega. This is what I have, and that's my U. Now this is a vector. That's a vector right there. And I can continue with my definition of addition once more. That gives me x1 plus parenthesis x2 plus x3. Same thing with the second component. And the good news is x1, x2, x3 are real numbers, and there is associativity in R. So I can move my parentheses from x2, x3 to x1, x2, and I end up with x1 plus x2 parentheses plus x3 comma, same thing with the second component. And I start breaking the vector apart using my definition of addition of vectors in R2. So this gives me x1 plus x2 comma 2x1 plus 2x2 right here, and I'm left with x3 comma 2x3. And I continue further and use my definition of vector addition to break this first set, and that gives me x1 comma 2x1 plus x2 comma 2x2, and this is in parentheses, so I end up with U plus V parentheses plus omega, which proves associativity under addition. 3 down, 7 to go. Axiom number 4 has to do with existence of an additive identity. Define the 0 vector to be 0, 0, which is actually the 0 vector in R2. Then for every element in S, and the element is of the form x, 2x, x comma 2x plus 0, 0 equals x comma 2x, which equals 0, 0. So 0, 0 indeed is the additive identity in S. Property number 4 done. Property number 5, we have to prove the existence of an additive inverse. Pick an arbitrary element t which equals x2x in S. Then negative t is negative x comma negative 2x. Remember, negative t is the same as negative 1 times t, and using the definition of scalar multiplication in R2, that gives us negative x comma negative 2x, and t plus negative t gives us 0, which is the same as negative t plus t. So that tells us that negative t is the additive inverse of t in S. That actually concludes the 5 properties under addition. The next 5 properties are properties with respect to scalar multiplication. Property number 6. Let x2x be an arbitrary element in S. I have to prove closure under scalar multiplication. Alpha times x into 2x is the same as alpha x comma 2 alpha x. And again, we are just using the definition, the standard definition of scalar multiplication here. And that equals x wiggle comma 2x wiggle, where x wiggle is alpha x. Alpha is a real number, x is a real number. The product of two real numbers is a real number. So my last vector is an element in S. And that proves closure with respect to scalar multiplication. Remember, to show that a given set is a vector space, you have to verify all 10 properties, or 10 axioms. 6 down, 4 to go. Property number 7. We have to verify left distributivity with respect to scalar multiplication. So alpha into u plus v is the same as alpha into x1 to x1 plus x2 comma 2x2. So the first thing I want to do is I want to use my definition of addition in R2, the standard definition, do not forget. So that gives me x1 plus x2 comma 2x1 plus 2x2. Use my standard definition of scalar multiplication. Alpha goes in. All the terms are multiplied by alpha. I use my definition of addition again, standard definition of addition in R2, and I break this down to alpha x1 comma 2 alpha x1 plus alpha x2 plus 2 alpha x2. I use my definition of scalar multiplication, standard definition to be precise, and I pull out my alpha. That gives me alpha into x1 comma 2x1 plus alpha into x2 comma 2x2, which is alpha u plus alpha v. And this proves my left distributivity property. Right distributivity property, axiom number 8. And again, do not forget alpha and beta are scalars and u is a vector. So alpha plus beta, remember alpha is a real number, beta is a real number. The sum of two real numbers is a real number. So alpha plus beta is just a real number. So I'm going to use my definition of scalar multiplication. Again, to be precise, my standard definition of scalar multiplication in R2, and alpha plus beta goes in. It becomes alpha plus beta times the first component, comma, alpha plus beta times the second component. Now there is distributivity in R because alpha is a real number, beta is a real number, x1 is a real number. So by right distributivity, we have alpha x1 plus beta x1, and same thing with the second component. Now I use my definition of addition, once more standard definition of addition in R2, and break this down to alpha x1 comma 2 alpha x1 plus beta x1 comma 2 beta x1. I can pull out my alpha using the standard definition of scalar multiplication, pull out my beta using the standard definition of scalar multiplication, and I end up with alpha u plus beta u. And this proves my right distributivity property. Property number 9, associativity property. Again, do not forget alpha and beta are scalars and u is a vector. So alpha parenthesis beta, u is alpha into beta x1 to x1. Beta goes in first using the standard definition of scalar multiplication. So that's alpha into beta x1 comma 2 beta x1. Now alpha is free to also go in, again using my standard definition of scalar multiplication. This is alpha beta x1 plus 2 alpha beta x1. Now alpha beta is a component, so I can pull out alpha beta together and that gives me alpha beta into x1 comma 2x1. Once more, I just use the standard definition of scalar multiplication. So we end up with alpha beta u, and this proves that our set S satisfies axiom 9. And finally, axiom 10, scalar identity. 1 times u is the same as 1 times x1 comma 2x1. Recall that 1 is a scalar, so using my definition of scalar multiplication, once more, standard definition of scalar multiplication. And I'm emphasizing standard because in class, I'm going to give you a few problems where you would be asked to use a different definition of addition and scalar multiplication to verify if a given set is a vector space. And the definition will not be the standard definition in that particular set. But we'll come to that when we get there. Let's continue this problem. So 1 goes in by the standard definition of scalar multiplication, and this is 1 times x1 comma 1 times 2x1, and 1 is a real number, x1 is a real number. We know what happens if a real number is multiplied by 1. So that ends up with x1 comma 2x1, which equals u, and we can also verify that that's the same as u times 1. And this proves the scalar identity axiom, and thus we can conclude that S, as defined above, is a vector space. Thank you very much.